Hi everyone. Our senior design project is the expulsion of small diameter devices from torpedo tube cartridges. This project is sponsored by Newick. We are Team ME77 and we worked alongside MEM Team 9. Our faculty advisor is Tianfeng Liu and we worked with Doug Merrick over at Newick. To summarize, this has been an R&D project to create a capsule to be stored alongside Mark 48 torpedoes within a Virginia-class submarine. This capsule utilizes the cradle, loading, and firing mechanism already on board. Our requirement was to create a design to launch multiple 3-inch by 39-inch projectiles in a volley fire style within the submarine's max performance envelope. This is meant to be used for countermeasures and special operations packages. Our full deliverables include full CAD and CFD packages with a 1/7 scale 3D print model and a 1/3 scale dual barrel test apparatus.
In order to meet these deliverables, we split our projects into 3 phases: research, design, and prototyping. That being said, the first step of our project was to research the launching method that would best suit our project. After design and customer considerations, which included factors such as simplicity, ease of manufacture, and design, as well as effectiveness, cost, size, and reliability, we determined via a Pew matrix that the hydraulic launching method would be the most effective. The simple design of the hydraulic method allowed for a more durable and reliable design that would be intuitive to use while still being the easiest to repair. The valve actuation method was also looked into. After extensive research and another Pew matrix, it was determined that the rotating disc with a cutout would allow for a simple design that would maximize the number of projectiles that could be loaded into the torpedo tube. In the middle of the cartridge is a watertight dead space that holds the electronic motor, which will then rotate to one disc at a time, creating a volley fire type of system.
With the research phase squared away, we moved on to the design. In the image below, we can see a model of the Virginia-class torpedo tube, as well as our module and the 12 projectiles that it's able to fire. Our module has a 12-barrel system that is, again, volley fired via the rotational plate valve. The projectiles are fired via a hydraulic impulse from an air turbine pump on board the Virginia-class sub through the slide valve when fired. The next design phase was the 7th scale and 3rd scale models. The 1/7 scale is a visual aid about 3 feet long, and the 1/3 scale test rig is a 2-barrel apparatus that uses a bladder tank as the simulated hydraulic impulse, and the rotational plate system will be able to choose between the 2 barrels via a stepper and Arduino control. The overall test rig was designed with a factor of safety of 2.2. Next, the prototyping phase came, and in the top of the slide, we see the electronics in the dead space that was mentioned previously, along with the rotational plate that will be able to actuate between the 2 barrels. In the low half of the slide, we have some 4th axis machining to help put the module together. The slots are used to facilitate the flow of water from the bladder tank and get a universal and uniform flow. In this image, we have the full non-submerged variant of the test rig. This test rig has a sacrificial patch as well as a checker pattern at the end of the barrels, which will allow us to quantify the exit velocity. In addition to this, we have the impulse system, which is a blue well water bladder tank that has a maximum flow of 2 gallons a second at 95 psi.
For our testing, we did high pressure testing with a max input pressure of 95 psi. We had outputs of a flow rate of about 119 gallons per minute and an exit velocity of approximately 63.5 feet per second.
Here displays a video of a plastic projectile firing out of the test rig. We tested projectiles made of aluminum, plastic, and steel, which all approximately traveled at 50 feet per second. This allows us to claim that the water travels at steady state. In order to validate our testing results, we then conducted ANSYS simulations of the test rig.
A simplified SOLIDWORKS model of the test rig with an accurate interior geometry was created for ANSYS work. The ANSYS Fluent setup includes the pressure-based solver. For the viscous model, we used the K-epsilon model with the preset model constants and the enhanced wall treatment option. Using the highest achievable flow rate of 2 gallons per second, the exit velocity of the projectile was found to be 60 feet per second. Measured projectile velocity from testing was 63.5 feet per second, which is about 5% from the expected ANSYS value. The full-sized design is simulated in the same fashion as the test rig using ANSYS Fluent. Only one barrel is modeled, as the rotating disc valve allows for one barrel and projectile to receive the impulse at a time. The minimum required exit velocity for the 3-inch projectiles from the module was agreed to be 50 feet per second. The full-size module that we designed will eclipse that value and be able to launch in a salvo fashion. Thank you for watching our video. We hope you enjoyed our presentation.